Hello everyone and welcome. My name is Jason Gregerson. In this video we're going to talk about bounding the error in a Taylor polynomial approximation. So our problem statement is this. Approximate 1 over e, the exponential number, using the fourth degree Taylor polynomial of e to the negative x, centered at a equals 0, and establish a bound for the error in our approximation. So our first step is going to be approximate 1 over e. To do this, I'm going to define my function to be e to the negative x and generate the fourth degree Taylor polynomial. So we've done that before where we used the series command and then the normal command to clean up the output and stored our result as a function. So when I evaluate this cell, I'm going to get the fourth degree Taylor polynomial for e to the negative x. But next I want to approximate 1 over e, or e to the negative 1. To do that, I'm going to have to evaluate my polynomial at x equals 1. In other words, I'm going to have to look at Taylor polynomial of 1. And when I do this, the output, 0.375, should be the approximate value for 1 over e. Now, it's not exactly 1 over e. It's just an approximation, so there is some error in this approximation. Now, just looking at this, I don't know if the error is 0.02 or 3.02. I'm not sure at this point. But calculus does give us a formula for establishing a bound for the error. In other words, the error has to be less than or equal to this equation, m over n plus 1 factorial times the quantity, the absolute value of x minus a, raised to the n plus 1 power. So we have our formula here, and we should already know the values for n, x, and a just from the problem statement. N is the degree of the polynomial we used to approximate. So we used a fourth degree Taylor polynomial, so that means n plus 1 should be 4 plus 1, or 5. So I have 5 factorial in the denominator, and I'm raising this quantity to the 5th power. A is where my polynomial is centered. I know my polynomial is centered at 0. Well, what about x? Well, x is where we had to evaluate our polynomial to actually get the approximation for 1 over e. So in this case, I had to plug in x equals 1 to approximate 1 over e. So we plug all these values into our error bound, and we get the simplified statement of m over 120. So we're told that the error has to be less than this number as long as we choose a value for m that is greater than or equal to the maximum value of the n plus 1 derivative on the interval from a to x. So in our specific example, we need to choose a value that's bigger than the 5th derivative, and these should be square brackets for derivative, bigger than the maximum value of the 5th derivative on the interval from 0 to 1. So how do we find that maximum value? Well, the first thing we want to do is actually plot that 5th derivative. So in Mathematica, I can look at a plot of the absolute value, ABS, of the 5th derivative, 1, 2, 3, 4, 5, on this interval from 0 to 1. And so now when I'm looking at my plot, I see that it looks like the biggest value is somewhere around 1. But what I could do is I could just say, let m equal 2. The number 2, based on my graph, is clearly bigger than any value of the 5th derivative on this interval. So as long as I choose an m that's bigger than all these values, it should give me a valid bound. So if I use that value for m, and now I actually plug that in to find out what my error bound would be using that m value, I'll put a decimal in to get a decimal out. Looks like I have an error bound value of 0.016 repeating. Now what does that actually mean? Well, if I'm approximating my value to be 0.375, this value could be over the exact value, but could only be over by at most that much. So in other words, if I subtracted that error bound value, then this would represent the lowest possible value that 1 over e could be. At the same time, my approximation could be under the exact value, but it could only be under by as much as that error bound is. So then if I looked at this value plus my error bound, I would get an upper bound for where the number 1 over e could live. So in other words, without actually knowing what 1 over e is, I know that it has to be somewhere within this interval. Now, of course, using Mathematica, we can actually calculate a value for 1 over e and verify that it really is inside of this interval. And sure enough, the exact value is 0.367879, so on and so forth. Now, I just chose the value m equals 2 because graphically I knew that 2 was bigger than any value of the fifth derivative on this interval. But there are smaller values for m that would still be above this value. So by choosing a big value for m, I have generated an interval that is correct, but it's not the tightest interval I could create. I could actually find an error bound that was smaller than this error bound, but would still be true if I chose a better value for m. Now m has to be greater than or equal to the maximum value of this derivative on the interval. So if I actually calculate what the maximum value is and use that for m, then I would get the best possible bound for the error in my approximation. So looking at my graph again, I can see that the fifth derivative is decreasing on this interval from 0 to 1. Well, that tells me that it takes its maximum value over here at the left-hand side. So I know the maximum value of this derivative on this interval would actually be the absolute value of the fifth derivative evaluated at 0. And that's what that maximum value would be. So now if we choose that value for m, and we'll put a decimal in to get a decimal out, then we'll get a new error bound that's smaller than our previous one, and we'll generate a tighter window where 1 over e must live. So now I can see that here is a tighter error bound for my approximation. So in general, we want to use the best value for m to get the best error bound. So we can see finding m can be the most challenging piece. I need to find the maximum value of the n plus 1 derivative on the interval. In our specific example, we saw that it was decreasing on the interval, so the maximum value would be on the left side of the interval. I could have a situation where my n plus 1 derivative was increasing throughout my interval. In that case, I would just evaluate my n plus 1 derivative on the right side of the interval. But there are some cases where my n plus 1 derivative wouldn't be increasing or decreasing. Let's look at another example. This example is very similar to our first example, except now we're taking our function e to the negative x and multiplying it by sine of 2x. And we're going to use that polynomial to approximate not just 1 over e, but sine of 2 over e. So essentially our workflow is going to be exactly the same. I just have a new function to work with. But I still need to calculate the fourth degree polynomial centered at 0 for that, and then evaluate that polynomial at 1 to approximate sine of 2 over e. And so when I do that, I get the following values. Here's my fourth degree polynomial, and here is the approximation for sine of 2 over e. But now I have to find an error bound for my approximation. Once again, the workflow is very similar to what I've done before. I have my formula for calculating the error bound. And since I'm still using a fourth degree Taylor polynomial, I'll still be dividing by 5 factorial and raising x minus a to the 5th power. And my polynomial is still centered at 0, and I'm still evaluating it at 1. So when I run this cell, I'm going to get that same general expression for my error bound, m over 120. And just like before, to find m, I need to find the maximum value of the fifth derivative on the interval from 0 to 1. However, when I plot that fifth derivative in this case, I'm in a different situation. Now I can see that the maximum value occurs sometimes inside of my interval. So I can't just evaluate this on the left or the right-hand side. So how do I find this maximum value? I can do calculus 1 optimization. In other words, to find the maximum value of this function, I would take the derivative of it, set it equal to 0, find the critical points, and evaluate the function at the critical points. So this is the fifth derivative, so to take the derivative of that, I need to calculate the sixth derivative. And I need to set that equal to 0. And I need to solve this to find my critical points. To solve this, I'm going to use the find root command to find a numerical solution. And as a starting point for my algorithm, from the graph, I'll choose the value of x equals 0.2. I'll get this for my critical point. Then all I have to do to find the maximum value of my function is evaluate this fifth derivative at that critical point. So I will copy that value, I will paste it down in here, and then I'm trying to find the maximum value of the absolute value of the fifth derivative. So this should be my maximum value, and this should be what I need to use for m. Now generally when I'm doing this Calc 1 optimization technique, I would also have to evaluate my function at the endpoints of my interval and at any other potential critical points inside the interval. But because I can see what my graph looks like, I know the maximum value occurs at this critical point. I know that's bigger than the function evaluated at the endpoints. So my graph helps streamline my process of Calc 1 optimization. Now the other thing I could do is use the built-in command, find maximum. To use this command, first argument is the function I'm trying to find the maximum of, which in this case is the absolute value of the fifth derivative. And then I have to give find maximum a starting point for the algorithm. In this case, I will choose 0.2 again. And when I evaluate this one, not only will I get what that maximum value is, the value I'm going to choose for m, but I also get where that value occurs. So whether you use the Calc 1 optimization technique or the find maximum command, we have to do some sort of optimization to find the correct value, the best value for m in this case. All right, so in this video we've seen how to use the formula to establish the best error bound when using a Taylor polynomial approximation. All right, that concludes this video. Thanks for your time.